Good morning. Um, what we have today is a set of problems that came from a final exam from some number of years back. So just like we looked at these sampler problems for the midterms, here is a sampler set of problems for a final exam. Now, for the final exam, the format on this exam and what will likely be the format on our exam is 8 questions, but they don't have any separate A, B, C, D portions to them. So they're a little different from the midterms because of that. There are more problems, but there aren't as many parts on each one of the problems. And so sometimes students are a little concerned that there's going to be 8 questions on the exam, on the final. But over the years, this has worked quite well, and it's turned out that the averages on the final tend to be about what the averages have been on the midterm. You know, not that, of course, some students are going to do a little better, some students might not do quite as well on the final, but in any case, the averages work out to be roughly the same. Now, one difficulty in putting together a final exam for a course like this is this has been a full semester. We have just gone through so many different topics, and so of course it's not really practical, not possible to have a series of questions that fit within the allowed time that really cover everything that we looked at. So going through this sampler final, I think it's useful just to get a feel for what a set of problems might look like on a final exam. But our final is definitely going to be different. And so don't go through these problems. This is a good set of problems to review from, but these aren't going to be the problems on our final. So think more broadly. So what you want to do is, in addition to taking a look at these problems, look at the problems that were on the sampler midterms, look at the problems that were on the actual midterms. Go back and look at the midterms that you've taken during the semester. And then, as time allows, go back and look at homework problems and go back and look at examples from class. So again, as much time as you have to put into the final preparation, go back and review all of the different materials. And I do think that the homework set, the sample problems within the lectures, all of those things are useful. And then if questions come up, stop by office hours or go back through the lecture notes and the textbook and work from those. So with all that said, let's go ahead and get a look at these problems. The first problem here deals with, it's looking at Earth's atmosphere. The air that we breathe is 78% nitrogen, that's N2, it's diatomic, 21% oxygen, that is O2, that's also diatomic, and then about 1% argon. So here are the molar masses, and these are the molar masses of the molecules. So the N2, each N has a molar mass of 14, N2 would have a molar mass of 28, is the way that worked. Oxygen, each oxygen has a mass of 16, and the combined mass then would be 32. Let's see. What the problem's asking about is calculating a density of air at a pressure of 101 kilopascals, now that's atmospheric pressure, and a temperature of 20 Celsius. So, you know, if you're outside and it's kind of a nice, pleasant day, and it's atmospheric pressure, how dense, what's the density of air under those conditions? Well, for that, we know we're going to get a good approximation if we are using the ideal gas law. So the ideal gas law provides a good representation. The numbers we get from using the ideal gas law for these compounds at these sorts of temperatures and pressures are going to be very, very reliable, within, probably well within 1%. So let's go ahead and do that. What we can do is we can take the ideal gas formula, PV equals nRT. Now, in there, we've got to find density. So the way we derive this and bring density into the formula is we can take the number of moles and replace that with the sample mass. So that's the mass of the entire sample, and that's always a little bit confusing. Is this the mass of just one atom or molecule, or is it the mass of the entire sample? And this was the number of moles of the entire sample. So we're going to take the mass of the entire sample and divide through by its molar mass. That would give us the number of moles. So now it's little m over big M, RT, and from there we can look for little m over V, the total mass of the sample divided by the total volume of the sample. When we take this formula, the ones on the ends here, and solve for m over V for density, it gives us pressure times molar mass divided by big R divided by T. And so let's put all the numbers into this. Now the temperature that was given, we have to convert that into kelvins. That works out to be 293 kelvins. And then the pressure given was 101,000 pascals. So here's my temperature, here's the pressure. And then the one thing left to do is to come up with a molar mass. What would be the molar mass averaged over these three compounds? Now, when we give percentages like this, these percentages are actually given in numbers. So if I took out, on average, if I took out 100 molecules of air, I would find on average 78 of those are nitrogen, 21 of those are oxygen, and one of those would be an argon. So what we can do is say, if I took a mole of air as a sample, well, you know, I count them out, 6.022 10 to the 23rd molecules of air, what I would find is that 0.7 moles of those would be N2, 0.21 moles would be O2, and 0.01 moles would be argon. So that's what I've done here. I've imagined 1 mole of air, and then I've taken the fractions of that 1 mole for each of the compounds, multiplied by the molar masses that are given, to find out how much mass 0.78 moles of nitrogen would be. And that would be 21.84 for the oxygen, 6.72 for the argon, 0.40. And so adding all those together would give me the combined mass of my 1 mole of air. And that number worked out to be 28.96 grams per mole. That's the big M here. But in the formula here, I'm going to need standard units. And so it looks like what I did was I wrote this up in the corner here. So this is what I'm getting from directly adding these numbers of grams. And then this would be the value in kilograms. This is the one that needs to go into my formula. The density works out to be 1.20 kilograms per cubic meter. Okay, and I guess it could have been left in grams. It could have been as grams per cubic meter. I went ahead and put it in standard units. All right, let's see what else we've got here. There's another problem. This is from thermodynamics. Here's another example from thermodynamics. We have a sample of helium. It consists of 2 moles, and it's going to expand adiabatically. It's going to start off at a pressure of 500 kilopascals and a volume of 12 liters. And it's going to end up with a final volume of 30 liters. So what would be the initial and the final temperatures of the sample? And I can't believe I didn't do a PV diagram on this. So I've got to go back and add, I've got plenty of room here. Maybe I'll go back and add a PV diagram into that. Okay. So, in any case, let's write down some of the stuff that we do have here. There are 2 moles. The starting pressure is at 500 kilopascals. So the 500 kilopascals is given, and then the liters I converted into cubic meters. So I'm getting everything in standard units here, although I don't necessarily have to do that. We'll see how this works out. So again, using the ideal gas formula, what we can do is go through and solve for what's my starting temperature. And the starting temperature would be equal to the initial pressure, initial volume, divided by N, divided by R. These should be P naughts and V naughts that are going in here. And I need to be using standard units for all of these. And then big R is going to be, in standard units, 8.314 joules per mole per Kelvin. And this worked out to be 361 kelvins. So the sample of helium that I'm starting with, and I always think it's a little funny to talk about these samples in terms of numbers of moles, but that's what we're given in the problem. So somehow I always want to know how we measure out 2 moles of helium. Does it turn into just doing some kind of a mass measurement, or what is it that we end up doing? And maybe it's done this way. Maybe it's done using the ideal gas law. In any case, the initial temperature that we would have for this sample with the information given would be 361 kelvins. And then what's going to happen here is I'm going to bring out the super adiabat formula. And the super adiabat formula relates ratios of temperatures, ratios of pressures, and ratios of volumes, and ratios of pressures along an adiabatic process. And that's what this is. So if I diagram this out as a PV diagram, the sample is going to follow an adiabatic path as it expands. Let's see what we've got here. I didn't include the pressures. It turns out there was enough to solve the problem just from working from the volumes before and after. We were given both volumes before and volumes after. So I did this in terms of ratios. Now, when I'm working in terms of ratios, the volumes, I can work in terms of liters. I just have to make sure the units match top and bottom on those volumes. As long as the units are matching, the units will cancel out correctly. Now, with temperatures and with pressures, with temperatures I have to make sure that these are absolute. And so we end up working in terms of Kelvin. Celsius won't work. Ratios in Celsius aren't the same thing as ratios in Kelvin. And in these formulas, the temperatures need to be directly proportional to the total energy, or the kinetic energy of the molecules. So the temperatures would have to be in Kelvin. Celsius won't work for these ratios. In any case, working from the super adiabat, what I did was helium is monatomic, and so in the super adiabat, on the volume term, that is taken to the R over CV power. CV for a monatomic is 3/2 R. So this works out to be 2/3. So it's 12 liters divided by 30 to the 2/3. I ended up with 196. Now what I'm watching for in this example is, it was an adiabatic expansion. If it's an adiabatic expansion, I would expect that the temperature is going to drop during that process. So, and the temperature that we're ending up with seems pretty reasonable. Oh look, there's the PV diagram right there. I didn't see it the first time. So here is the PV diagram for what we've calculated. And here's the pressure, here is the volume. Definitely practice drawing the PV diagram. You guys know, I think from the midterms, we must have had 1 or 2 show up there. There's just got to be one coming up on the final. So here is the PV diagram for this setup. And what I've placed in here is a couple of isotherms. So using the ideal gas formula, I've written in a couple of isotherms. Now one of those isotherms is representing the starting temperature, 361 kelvins. And the other isotherm is representing 196. These aren't minus signs here, these are just part of the isotherms. So 361 kelvins, 196 kelvins, and an adiabat would take us along a smooth curve that gradually drops through a series of isotherms. If there's an expansion, then that's what we have. If it was a compression, that would be the opposite. But we're going to drop from that higher isotherm when we're at 12 liters By the time we're at 30 liters, this adiabatic process has dropped the temperature down to this 196 Kelvin adiabat. So that's what's going on in the PV diagram. Yeah, it's a good thing to get that drawn in. All right, questions on any of that? Yeah, I didn't see the PV diagram at first either, but apparently it was there the whole time. So there it is. All right, moving on to problems 3. So those 2 problems represent all of thermodynamics. So you can see, as we were saying, that I'm trying to pick problems that represent really important topics, maybe a broad range of topics that need to get included, but it's hard with just a limited number of problems and a limited amount of time on the final. So on problem 3, we are looking at a ring of charge. So there's an object that's shaped in a ring, it's circular, and there's charge uniformly distributed along the entire ring. It says that the total amount of charge is 70 nanocoulombs, and that the radius of the ring is 3.5 centimeters at a location of 8 centimeters at a distance of x along the axis. Determine what would be the electric potential and the electric field. I know it's like I slipped 2 questions in there, but I didn't put it as A and B, so it must only be 1 question. Let's see. So here is the ring, and it's got that charge on it. And what we did all through the semester on these problems, I hope these look pretty familiar. We've looked at a number of examples like this. Is we broke the charge down into little bits of dq. And a little bit of dq is going to form a little bit of electric field for us. So, and the electric field that we end up with is going to be directed, it's a vector, it's going to be directed away from the dq. And that says that we are going to need to divide that into components. Now, as we integrate around the circular loop, what's going to happen? Here's our integration right here. So if I add together all those little bits of electric field, I'll get the combined electric field. And the little bits of electric field are going to be given by the electric magnetic force constant, little k, times dq, divided by r squared, divided by the distance squared, times the cosine theta. That's the component we're going to keep. The sine theta components are going to cancel out. So all we're going to be left with is the cosine theta component. We could try carrying out the integration on the sine thetas. It's going to integrate out to be 0 if we've done it properly. So let's see how this is going to work then. The numbers we've been given, I'm calling this big R to be 3.5 centimeters. So that would be 0.035 meters. And the x value that we're looking at is 0.080 meters. So I guess they asked about the potential first, right? I forgot. And so the potential here would be given by kq over r. And for the potential, all parts of the charge, all parts of the ring, all of the charge is actually the same distance from that point. So it doesn't really make a difference. It does not make a difference the fact that it's spread out around a ring. As long as all the charge is the very same distance, then every little piece of charge is going to get divided by the very same distance. So when I add up all the charge divided by distance, for the potential, I'm going to get little k times q times r. Now remember, little k, I didn't write it down here, is 8.99 times 10 to the 9th. It's that force constant, the electric and magnetic force constant, that we've used throughout the course. I mean, we used this for 12 weeks or so. So we've been using this forever. It showed up in chapter 21, and we've been using it consistently through chapter 31. I guess not when we were doing circuits. But little k is right there. Times q divided by r gives me 7,210 volts. And you guys have done enough of these problems now that you know that if we play around with the distances and the amount of charge. This was, well, it was only 70 nanocoulombs, right? That's not an enormous amount of charge, but we are pretty close. We're only a couple centimeters away, and we're ending up with, 7,210 volts, which looks like a pretty big number. To get the electric field, what we're going to do is we're going to integrate again. Now, remember, the R's are constant. So the R's just slip right through the integration sign, as does the K. All we're left to do is to combine all the charge together. So this is one of those examples that we looked at, I think this is back in chapter 21, where we're really just adding the Q's at the end. There's no need to integrate over the charge, over the distance. We do not integrate over the angle. The angle is not changing, the distance is not changing. And so as a result, this becomes KQ over R squared. Now for the cosine theta factor, what I did was I multiplied by X over R. Those two factors need to get joined together here. So cosine theta would be X over little r. And so that would be the total formula. The formula for this would be K times Q divided by little r squared times X over R. Here's the integration for the potential. So I did start out with K dQ over R, brought out the K and the R because they're both constants, and then just integrated the Q's. And adding up all of the charge together gives us the total charge. So that's it. The electric field works out to be 75,700 newtons per coulomb. Again, it's a large number here. The little r values were pretty small. The little r's I calculated in terms of big R and X, worked out to be 8.73 centimeters. So not too far. I guess it's not, the ring is 3.5 centimeters. The distance is actually, between 8 and 9 centimeters. So, a distance like that, maybe. So here's my charge, here is the ring, here is the charge located right there. And the ring is not too big, something like that. All right. All right, let's take a look at problem 4. So on problem 4, it says that we've got 3 capacitors. The capacitances are 6 nanofarads. How many different ways could they be connected? Show diagrams showing combinations of these capacitors where the net capacitance would be 18. And then show configurations where the net capacitance would be 9 and 4 and 2. Now, from working with capacitors and solving a bunch of problems in capacitance, what we saw was to get the capacitance to get higher, we would place the capacitors in parallel. So the first thing I tried was just putting them all in parallel. And sure enough, if I put them all in parallel, the individual 6 nanofarads are going to add up to be 18 nanofarads. So 3 times the capacitance, and where the capacitance is 6, gives us an 18. The other extreme, I thought, was what would happen if we put them all in series. Well, if they're all in series, then 1 over the net capacitance would be 1 over capacitor 1, plus 1 over capacitor 2, plus 1 over capacitor 3. That would be 1/6 plus 1/6 plus 1/6, which would be a half, would be 3/6, would be a half. And then we have to take the inverse. So carrying out that calculation for series capacitors gives us 2 nanofarads. So that's the 18, that's the 2, those are going to be the extremes. Now the numbers in the middle are going to be some combination of capacitors in parallel and series, so some combination of that effect. And so that's what I went to next. What I did was I tried putting a 6 in parallel with the other 2. Now, those 2 capacitors in series, if I use the formulas, are going to have a net capacitance of 3. I'm going to end up dividing the 6 by 2 and getting a 3, and then 6 and 3 combined would be 9 nanofarads. Now I could move the individual capacitors around, but they're all the same. So since they all have the same capacitance, those are not going to give us any different numbers. And then finally I was thinking, okay, the last one I don't know why, but I thought, okay, what if we start with a pair in parallel and then add the third one in series? Here we started with a pair in series and added the third one in parallel. So I finally thought, oh, that's how we would do this. So I put 2 in parallel, added a third one in series. So these combined, those 2 6s combined are 12. And then there's a 6 that's in series with it. So 1 over 6 plus 1 over 12, that's 3/12. When I take the inverse, we get 4. So those look like all the combinations where we've used all 4 capacitors. And those are the values that we've ended up with. Okay, if you guys come up with other combinations, let me know. Maybe there are some where, let me know if you guys come up with other combinations that I've missed. Okay, I'm going to go ahead and move on. So now problems 3 and 4, the ones we just looked at, actually I'm going to go back. So we know we had those 2 problems from thermodynamics, and now what we've got is we've got 2 problems from looking at electric fields and that early chapter on circuits where we first introduced capacitors. So this is kind of from the first 4 weeks, first midterm. These are from the next 4 weeks, the next midterm, and I'm guessing that's the pattern that will continue here. So we've got a couple problems from chapters 25 through 28, which would be some more circuits, and it would also include magnetic fields. So let's see what we've got here. What it says is we want to find out the magnetic field surrounding a wire. Now the wire has a current of 3.7 amps, and it's formed into a single circular loop. Now it's good there's only one loop, because I always forget to put the number of loops into my problems. So if there's just one, I'll be okay. So what I did was I did draw a diagram here. Here is one circular loop, and there's current going through it. Now why is there, these problems always drove me crazy, right? I thought, why is there current going through that loop? And that's because it's hooked up to a battery or something. So the current is not just going through the loop on its own. Something's got to be driving that current. This is not a problem in generating an EMF, and so so don't get those mixed up. So read the problems carefully. In this one it just says there is a current going through a loop, and we want to find out what is the magnetic field due to that current. And so somewhere here these wires separate and come over, and there's a battery, and that's what's driving the current, and so there's 3.7 amps going through that. And the magnetic field here, this is our magnetic field formula when we're carrying out integrations of the magnetic field. So little k, the electric and magnetic force constant, times the current divided by 2 factors of c, and then I have to integrate along the path. So the integration is along the path of the current, and I have to divide through by distance squared. And then there's a cross product of unit vectors. One of those unit vectors is in the velocity direction, which we will relate to the direction of the current. And then the other unit vector is in the radial direction. So let's get ourselves oriented here. This is an example we looked at in class. It's a good example in setting up these unit vectors and determining the direction of the magnetic fields that are going to be generated here. So we know that the direction of the magnetic field is determined by the direction of this cross product. So the first thing we want to do is get the directions figured out. Once the directions are figured out, we can drop all the vector signs. We don't need them anymore, we just need them to figure out what direction the magnetic field will be in. And so, so let's do that. So I'm going to take a short segment. I'm going to take a little segment of the current length, ds. So ds is oriented along the length of the current. And what we're doing is we're saying, due to a little bit of current right here, that's going to contribute to the magnetic field here. And then we have to integrate along the entire path of the current. We have to imagine going through and one by one taking a look at every little DS, every little short segment of current is going to help contribute to a magnetic field. Now, one possibility, if we were looking at the electric fields of charge, for example, we would start to get cancellations. But the magnetic field is oriented differently. So when these charges are in motion, what we can do is we can identify, starting at the source, which is the current, and heading towards the location where we want to measure the magnetic field. I want to measure the magnetic field here. This is what's causing the magnetic field. This is its source. So I go in that direction, and then at the location where I want to carry out this cross product, the unit vector, the radial unit vector, is going to be directed away from the source, away from the DS. And so that's what gives me the radial direction, something pointing away from the current that we're looking at. Now the velocity unit vector is going to be in the direction of the velocity. I don't think in the problem they told us which direction the current should be going in, so I had to add that on my diagram. So on my diagram, I had to be able to show what direction is the current traveling in. I decided the positive direction would be the easier one to go with, so that's what I picked. And so that gives me a velocity vector here in R. Now as I integrate, as I go around this loop and integrate, the V and the R unit vectors are going to remain perpendicular to each other. So that says that when we carry out the cross product, the magnitude will be 1. So the cross product, once we get the direction figured out, the cross product we can just drop out. It's just a factor of 1. We don't need it anymore to include that. But let's get the direction. The direction is going to be, for the magnetic field, is the direction of the unit vector V cross unit vector R. So I'll put my thumb in the direction of the first unit vector, which is the velocity, and my fingers in the direction of the radial unit vector. Those are ER. And then my palm is facing in the direction of the magnetic field. So it says for current going in this direction, magnetic field at the center is coming out of the page. Now that's important because what that's telling us is as we integrate around the circle, we're not going to get any cancellation at all. Every little bit of that current length, every DS of current, every little bit of path is going to help contribute a little bit more to the magnetic field. And since all the magnetic field contributions are in this very same direction, we don't have components to keep track of. I don't have to keep track of sine theta or cosine theta components. The magnetic field is entirely in that one direction. So let's see what happened here. A lot happened. First of all, we identified the direction of the magnetic field. For the current going in the positive direction in the XY plane, the magnetic field would be in the positive Z direction. If the current I had chosen to go in the other direction, then the magnetic field would be into the page. But that's the setup, and yes, you have to show your work for this. So you can't just write down a bunch of formulas. You actually have to. I'm going to say, yeah. I mean, clearly, if you know, you have to show your work, and the work's going to include showing the unit vectors and the cross products and how this was carried out. So let's see what we've got. We've dropped the vector signs because we identified the direction. The cross product is giving us just a factor of 1. So I've got factor of little k, I, c squared. Now, I have to integrate, let's see, r, the distance is equal to big R, where big R was given as, did I get this right? It's a radius, it is, okay, good. Sometimes, you know, a lot of times these are given as diameters. But it is the radius. The radius was given as 7.3 centimeters. And so, there it is right there. Okay, that's the radius I want to use. And little r is equal to big R, and big R is a constant. Now integrating along the path ds, that's a path integration, gives us the total distance, and that would be 2 pi r. So bringing everything together, the factor of big R on top cancels one of the factors of big R below, and the magnetic field formula for this is going to be given by 2 pi k times the current divided by c squared 1 over r. Putting all those numbers in, I ended up with a magnetic field 31.8 microtesla. All right, questions on any of that? Okay. Any questions at all, stop by office hours. Let's go over that. Let's see, problem 6. So problem 6 is coming from some more of the probably chapter 25, right? This is something looking at some circuits. It says we have a light bulb. The resistance is 240 ohms. We're going to plug it into a 110 volt outlet. Now I think the standard voltage on outlets is 120, although you will see 110 volts listed in different places. 110 volt outlet, what's the cost of operating the light? Oh, we're going to use the light 1 hour each day for a year, and we have to update the electric costs, because my electric costs now are zero, actually. Put in a bunch of solar panels a couple of years ago, and so we put in enough solar panels that they produce enough electricity for all of our electrical uses that we have, and then we've converted a lot of our appliances in the process of converting all of them into electric. So we can run 100% electric off of our solar panels, or at least an equivalent amount of energy as to our solar panels. Of course, the solar panels only produce electricity during the daytime, and they do produce a lot more electricity in the summer versus the winter. Anyway, the cost here, getting back to the cost, 13 cents per kilowatt hour. I think the going rate now is like 20 cents. And I don't think this is that long ago. I think there was a big jump in electric costs over the past several years to reflect the more of the actual costs of producing that electricity. Let's see, so we've got a light bulb. It's got a resistance of 240 ohms. It's got a VRMS of 110 volts. Oh my gosh, I used leap year. So this must have been done during a leap year. I did 366 days instead of 365. All right, so I ended up with the amount of time that this light is on during the entire year is 1.32 million seconds. Really? I left the light bulb on for 1.3 million seconds this year. That's a lot of time that the light bulb was on. And then the power that we're looking at here is going to be given by V squared over R. So we're going to be using, when the light bulb is on, we're going to be using, it's a 50.4 watt light bulb. And the energy, I used U for energy because big E now is the electric field for these chapters. So the total energy usage for the year worked out to be 66 million joules. I used 66 million joules for this light bulb that was on just an hour every day. So millions and millions of joules here. Now, a kilowatt hour is the equivalent of 3.6 million joules. We had a lab where we looked at this. And we've had homework problems too, and we've talked about this in class. So they've given the cost in kilowatt hours. I went ahead and used standard units. So I decided to do everything in joules and then write the cost also in terms of joules. They're saying it's 13 cents per kilowatt hour. A kilowatt hour is 3.6 million joules. So this worked out to be $2.40. All right, so that's the cost, paying for the electricity used to light this bulb for the entire year. All right, problem 7. Problem 7 says, we're moving now into the last 3 chapters of the course, and problem 7 is looking at inductance. So what I've always recommended with these problems is, once we're through the whole course, which we are, headed in towards, the final exam, when you're given a circuit problem, the first thing I would recommend to look for is it an AC power supply? Is it a DC power supply? Or is there no power supply at all? Now, in this problem, it says that it's connected to a voltage source of 20 volts. Doesn't say anything about a frequency, does not say it's alternating. I'm guessing this is suggesting that it's a DC voltage source. So, a battery, it's a 20 volt battery, for example. Now, if a question comes up in an exam about any of this, just ask, okay? Don't spend a lot of time, spend a little bit of time reading the problem, making sure that you're reading everything carefully. But once you've read the problem carefully and you're still not quite sure about something in the problem, go ahead and ask a question on that. So here is the inductor and here is the resistor, and I'm moving ahead with my 20 volt battery. Now this is an LR circuit, and we've looked at LR circuits, and it says that the time constant for the circuit is 150 milliseconds. Now that's interesting because the time constant for an LR DC driven circuit is L over R. So they're kind of telling us, we've gone into the lab, we've measured the voltage on the battery, we've measured the current, we're getting 40 milliamps, and we've measured the time constant. So we've gotten out an oscilloscope and we've actually plotted what is the current as a function of time. Or similarly, we could measure what the voltage across the resistor is as a function of time. But here's our graph. So here is I as a function of time. And the time constant we've identified, there it is at 63%. So we brought that down and measured this on our graph, and it's at 150 milliseconds. And so what they wanted us to come up with is how much inductance do we have. So it says that the current rises to a maximum value. The current eventually reaches 40 milliamps. Now that's going to tell me what the resistance is. Once we close the circuit, once we close the switch, and operate this circuit, it's going to asymptotically approach a final current. And once the current settles down, it's like the inductor's not there. The only thing the inductor is doing here is it's preventing the current from immediately jumping to that final value. Instead of closing the circuit and having the current jump immediately to a value, the inductance within that circuit moderates the effect. It slows the process down to where there's some rate at which this is happening. And the formula that we went through and derived and we've used for these circuits, I naught 1 minus e to the minus t over tau. So to get the R value here, we can take the voltage and divide through by that asymptotic current, and that leaves us with 500 ohms. So there we go. The resistance in the circuit must be 500 ohms. How are we going to get the inductance? And the inductance comes from the fact that we've measured the time constant. So by taking this into the lab, measuring the time constant, we're able to say L is equal to R times that time constant. So I can take my 500 ohms, multiply by the 150 milliseconds, there it is, and I ended up with 75 henries. Now that's an enormous amount of inductance. That's a really big inductor. If you remember in the lab, those inductors we had in the lab were what? They were like, the really big ones. The big ones in lab were like a henry, right? Maybe a little bit more than a henry. So 75 henries that's a pretty good sized inductor. That is not a little inductor, that's a lot of inductance. I'm always saying check your numbers, and I completely understand if you did this problem and you saw 75 henries, and you're paying attention to numbers you've been getting in your homework, you're going to think, wow, that's really big. So of course you're welcome to ask about that too. But I did end up giving numbers on this problem that resulted in a large amount of inductance. Okay, let's get to this last problem here. So here's the whole entire final. Last problem says we have a resistor, a capacitor, and an inductor. This time, instead of a DC power supply, they have an AC power supply. It explicitly says AC power. It says it's at 60 hertz, and that the VRMS is 120 volts. That's a standard outlet, right? So all the outlets that we work from, the standard numbers on those outlets, the nominal values are 120 volts, RMS, it's an RMS value, and 60 hertz for the frequencies. That's how fast we spin the generators in the power plants. And so I've written down all of the given information: 750 ohms of resistance, 700 nanofarads of capacitance, and a more sensible amount of inductance, 1.1 Henry. We know the frequencies, and so I just went ahead and used the radiance frequency. Rather than writing it down in hertz, I took the 60 hertz multiplied by 2 pi to get the radians frequency, because that's what we want in the formulas. So the radiance frequency for this would be 377 radians per second, and there's the RC. And so what I can do from that is, I've got the resistance in the resistor, how much reactance is there in the capacitor, and how much reactance in the inductor. Basically finding out how much resistance we have in each one of the devices. Well, the capacitor is going to have 3,789 ohms of reactance. The inductor is going to have 415. So if I draw, here's the circuit, which looks pretty good. And then here is my impedance diagram. So on the impedance diagram, I've got the R drawn along that horizontal axis. I got the XL in the positive Y direction, the XC in the negative Y direction. And looking at my numbers, the XC is much bigger than the XL, much bigger. That's clearly going to dominate. So when I subtract off the XL, I'm still going to have most of this remaining. And then I can use Pythagorean's theorem. So I can take the difference between XC and XL. Here it is. I'm covering it up. So here is XL minus XC, and then that number gets squared. So I'm going to get cancellation between these two numbers, partial cancellation, and then that's going to get squared. And the Z value I ended up with was 3,450, 3456 ohms. And that's the Z value. So we've ended up, it is asking in the problem what, I've got to go back and read the problem, what is the phase angle between the current and the voltage? So the phase angle, the current's going to be on the phase diagram, using this impedance diagram as a phase, measuring phases. The current is going to be in the direction of the resistance, and the total voltage will be in the direction of the total impedance. So the phase difference between that, the voltage is lagging the current, that's going to be given by the inverse cosine of R over Z. I've got the R value, I got the Z value, I've got that angle. And so the angle works out to be 77.5. So I didn't really get this drawn entirely to scale, because again, the reactance in the capacitor is, well, it's like 5 times bigger than the resistance. So if I was drawing this to scale, the XC should be 5 times bigger than the R. And that angle is, as you can see, is much, it's a good sized angle. 77.5 degrees is really angled mostly downwards. But that's it. You know, that's the AC circuits. Questions on any of that? So again, I hope this is useful. I hope it's been useful to go through the problems. These are a good set of problems, but they are clearly not adequate in preparing for our final exam. So make sure you're going back over all the midterms that we've taken this semester. Make sure you're going back over the sampler midterms. And as time permits, go back through homework problems and go back through examples from class. So all of those are going to help prepare you for the final exam. And then of course, stop by office hours, and whatever questions you guys have, bring them in, and we'll get those questions answered. Good luck with all of your preparations for the final.